Okay, a couple of weeks ago I put on the internet my experiences of writing my first Z80 program, which just happened to be for the Mattel Aquarius, a computer that I'd owned since childhood. And I put together a simple little game and I was quite happy with it, and that was what was featured in the video. But I wanted to make it look a little bit more professional, and I wanted a loading screen. Now, I did have a loading screen on the original, but I decided to play around with it a bit more. Just so you know, in order to make these drawings, I'm using this online application, Aquarius Draw. And what it allows you to do is allows you to use the very limited Aquarius character objects to create a drawing. Some examples on here somewhere. There you go, you see. So it just makes it a bit easier to do some sort of graphic on the Mattel Aquarius. And so I had a go at doing that and produced an image. It was rubbish, but an image. Okay, and then once you've finished the image, what it does is it generates a basic program which then loads the image. So as you can see here, this is the program that loads the image, and then what it does is it creates a whole load of data statements that contains your image. So if we were to now to run that, you can see that it works. It's Aquarius Basic. It runs at the speed it runs, and it works very well, and it produces the image. But I wanted to do two things. First of all, I wanted to cut down on the amount of data that. Hang on, let me just see what to. That it was trying to save, because it seemed to me a little bit wasteful of memory. Because if you each block of the Aquarius, each character position is 1 byte of character memory and 1 byte of color memory. And if you look at the data statement there, you can see that it uses basically 3 numbers for every memory location. Now that can be 3-digit numbers, so you could in theory have 4 times 3, 12 characters for each byte of information. And so I wanted to, first of all, to figure out a way of compressing this information, but then I also wanted to write it in such a way that I would be able to then write a Z80 application to get the data back and fast. And this is the solution that I come up with. So what happens is that obviously I have to run the program to load the image up. But then what it does is there's a little subroutine that then goes through and it looks at every memory location, and it takes the byte information from the location. But what I then do is I split it into 2 bytes of data. And how I've done this is I've split it so that the top 4 bits of data and the bottom 4 bits of data are recorded separately as 2 numbers. Now these numbers, of course, would be 0 to 15. But even that doesn't really help us, because if you look, right, well, not help us directly, but anyway, if we go to the Mattel Aquarius manual. So if we were trying to save the data from 0 to 15 in a basic statement or in a string or something like that, we're in all sorts of trouble, because in here there's character strings which would seriously mess up your listings. I think 7's bell, 11's character, clear screen, there's a character return in there. So playing around with any sort of byte value under really 32, weird things happen. And then from memory also, if you go above 128, which is in this region here, and you try to save any of these bytes as well, again weird things happen, because I think that's when you start getting into the tokenization of the basic language. So again, not good. So what I decided to do is to take our numbers, which are from 0 to 16, and to add 65 to them, or 64 to them, sorry, and that puts us into this area here. So to save a 0 would be 64, and then 1, 2, 3, 4, 5, right up to 16 or 15. Okay, so that's what I was trying to do. Now that this is went through and loaded the program up, what I've been doing is taking a byte information, so this byte here, which let's just say is 32, splitting it into two separate nibbles, 4-bit codes, and then adding to each 4-bit code 64, and then saving the resultant character string to a string. Right, might make more sense if I show you the program. Okay, right, so let's see if this makes any sense to you. So this is the program that loads the graphic up as supplied by that website, the Aquarius drawer. So that actually loads the graphic, and then the next bit is the bit that I wrote to save the graphic. So if we look at this, there's three variables in here. There's L equals 0, which is going to be the length of the string that we're going, a temporary string that we're creating. Li, which is a line number, which will make more sense in a minute, and O string, which is going to be blank at the moment. The program's then going to loop through every memory location in the graphic and color area. Okay. First thing it does, it says, right, if O string equals blank, okay, then it makes O string equal basically the line number, which I guess is going to be 6000, plus a space, plus data, plus character string 34, which is a double quotation mark, and then it sets L to 10. Now L to 10 has been set because that's basically the length of that piece of information you got there. What then does is it checks the peak of the memory location that we wanted to save, and this is the bit that splits it into two. So C is the number that we're trying to save. So if we divide the number by 16 and integer it, that gets us our high 4 bits. Like I said before, we're plussing 64, so it puts it into that nice safe character area. So if this number was 2, 2 plus 64 is 66. 66 happens to be the character B. Okay, so it'll add to O string the character B, and then it'll do exactly the same thing with the low order 4 bits with that little bit there. So O string is now going to be 2 bytes longer, and those 2 bytes are going to be 2 alphanumeric characters which represent the graphical data stored in a single memory cell. L equals L plus 2 because the length of O string is now going to be 2 characters longer. What it then does is it says, right, if the length of O string is greater than 68, I think the maximum line length is 72 on an Aquarius. Might be wrong about that, can't remember now. It's been 2 weeks since I wrote this. Then what it does is it adds another double quotes to the end of O string, and then it L prints it. And it sends it to the printer, and then resets the O string back to blank, resets the length of O string back to 0, and it increases the Li, the line number, by 10. And it then goes back to the next character, and it does the same again. So every time it sees a memory address, it's adding 2 extra characters onto the printer stream, but then it's also putting these tidying up bits and bobs in as well. And then when it gets to the end, it writes the last line number, followed by data, followed by character string, followed by an X, followed by the character string of double quotes again. Now, because Virtual Aquarius allows you to capture the printer as a text file, what you then end up with is something that looks like this. This is a data representation of the graphic screen. So those two characters there represent the first character position, those two the second, the third, the fourth, and as it goes on. And that's all right. So basically in here there is encoded 2000 bytes of information. Now obviously this 2000 bytes is going to become 4000 bytes, and with the extra line numbers and datas and quotation marks, it's coming out to about 4.5K. 4.5K to save 2K, which is better than the other program was. All of this will make more sense at the end, why I've gone this convoluted route. Right, so the next stage was to prove that I could reload the data. And so I wrote this program here. So what we've got here is the bit of program that I wrote to prove it works, and then it's followed by all those data statements. Now, how did I get these data statements back into my program? Well, it was quite simple. All I had to do was use a quick type function, and the quick type function took all these data statements from the text file and dumped them back into the program. So there was no retyping information. Literally, it was all automated. And then when it runs and it pulls the data from those data statements and it produces an image. And what you will notice is, of course, that it's a lot slower, but it does work. So it comes through and it pulls. It's obviously pulling everything as a direct memory location order. So it's doing the character-based information first. There's then a slight gap, and then it'll pull the colour information through. Which it will very soon do. It's really slow. Really, really slow. But Basic's doing everything it can. And there it goes. Now it's adding the colour information, and we're getting our little screen through. Right. So what next? Well, the next was to turn it into Z80, and this is my solution. Let's see if this makes any sense. Right, this is the actual finished final program. So this is mainly the game, but if you remember from the first video, I had the game over as a huge dump of poke statements. Well, as you can see in this last version, I've actually just turned it into data statements, so that doesn't take up as much memory in the program either. Right, so how does it work? Well, how it works, how the machine code version of this works, is it uses a bit of a trick. Like I say, maybe people already know about this, but yeah, but anyway. The program is the program, and I've deliberately wrote the data statements for the data for the graphic to be quite a high number, so that it's always at the end of the listing. And that's because the Aquarius knows information. Right, it knows, for example, where basic program ends, and it ends in these 2 bytes of information here. So I can very quickly interrogate the Aquarius, and I can find out roughly where this memory cell is here, the very end of the data statements. right? So I know the memory address of that there. I also know that this listing is, I can't remember what it is exactly, but it's 4,500-ish characters. So I can tell the Aquarius, the Z80 machine code, to go back the 4,500, whatever the exact number is, memory locations, and that'll get the Aquarius back to about here. Okay, so then all the Z80 program does is it goes through and it reads the characters. So it'll read D, and it'll ignore it. A, ignore it. T, ignore it. A, ignore it. But then it gets the quotation mark. Now the quotation is a switch which turns the flag on and off in the Z80 program. And what it does in this case is it says, right, now we've got data. So then what it'll do is it'll load the G as a byte, and the G as a byte will be that's a bit small for me to read. 64, 65, 66, 67, 68, 69, 69, 70. So it's 71. So read it as 71. Okay, so now it knows that byte is 71. What I'm then doing is I'm ANDing it with 15, sorry, which has the effect of stripping off the top 4 bits of data and leaving only the 4 lower bits of data, which has the same effect of actually subtracting the number by 64. So our 71 will then become, brain seizure, 7. Okay. But then we need to multiply that by 16. And the best way of doing that in machine code is to shift the bytes, shift the bits 4 times upwards. And that's what it does. It shifts the bits 4 times up, which effectively multiplies it by 16. It then takes the next number, next character string, and it does exactly the same in that it strips off the top 4 bits to reveal the bottom 4 bits, but then simply adds it on to the number from the previous piece of information, and that gets us back the byte that we want. And then it stores the byte in the first memory location, which is there. It then increases the index by 1, and then it reads the 3rd and 4th, puts it into the second location, and goes along building like that. And it'll continue reading the data 2 at a time, turn them into bytes, poking them into the screen location until it hits character string 34, the double quotes, and that'll switch it off. So it'll switch off, 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 back on again, read the data, read the data, read the data, read the data, off, 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 on, and it'll continue through like that. And you're asking the question, does it work? And does it work fast? And the answer is, it works this fast, which I think is quite good. I think that's probably, it's less than half a second, I think. And that then gives me the introduction to the game, which I wanted. And then the game is pretty much as you remember from the first video, if you watched the first video. So that's my solution. Now, like I say, I don't know if this is a common procedure, but it's just what I worked out, and it seemed to work quite well. Because like I say, I think that's quite a fast little routine. It doesn't, well, it uses, you know, a low enough reasonable amount of memory that you're not wasting. You know, the Aquarius has got, what, about 18k memory? So if I'm losing 4.5k on this graphic screen, you know, that still leaves me 13.5k to play around with and write programs and do other things with. Or indeed have multiple graphic screens. So that's where I am. So that's the second program. well, not the second program, but the second bit of, well, the latest, well, a bit of Z80 that I tackled to do that job. There will be a third video coming soon. I'll say soon, it depends when I get around to it. What I'm working on now is another game, but all I've managed to do so far is work on the graphics routines. I haven't even written the game yet. This is purely just trying to get the graphics into a state where I can start to write the game around them. So what you should or shouldn't write. So yeah, come on. Let's go and do some graphics. There we are. So it's yeah. So the graphics routine draws these snake type lines on the screen, but this is definitely not a snake game. This is a different type thing which I'm working on. So far I've got what I want, which is this fast drawing routine, and now I need to write the game around it. There'll be one extra little bit of Z80 coding that I'm wanting to do as part of this, in that I want to create a sprite type character which hovers over the screen, and when it moves around the screen it can do so without destroying the background, and that's going to be recording the data underneath it, so that every time it moves it has the opportunity to put the data back that was there previously. That's the theory anyway. Right, okay, so until next time.